April 7, 1989, the Norwegian Sea, the Soviet nuclear attack submarine K-278, also known as Komsomolets, was patrolling deep beneath the surface. She was a singular creature, a unique machine designated by NATO as the Mike class. Unlike her steel sisters, she was forged from a high-strength titanium alloy designed to withstand pressures that would crush a standard boat into scrap. She was the only one of her kind, a prototype built to hunt at depths exceeding 3,000 feet. But on this morning, the enemy was not a NATO hunter-killer group or a pressure mine. The enemy was inside the pressure hull. The catastrophe began in compartment 7, the aftmost engineering space. A short circuit ignited a spray of oil mist, creating a sudden, violent flash fire. In a standard maritime accident, the crew might have contained the blaze. But physics turned against the crew of the Komsomolets. A high-pressure airline ruptured in the chaos, feeding the flames with a violent blast of high-pressure air. The result was not just a fire, but a blast furnace effect. The temperature in the aft compartment spiked to extreme levels, reported around 2,000 degrees, destroying cables, insulation, and control systems. The engineering team faced a binary choice. If they did nothing, the reactor controls would melt, and the boat would suffer a nuclear meltdown at depth. If they acted, they would likely die. They chose to act. They successfully scrammed the reactor, shutting down the nuclear core and securing the control rods. This decision saved the ocean from a radioactive catastrophe, but it left the boat without propulsion. With the fire raging and systems failing, the command crew executed an emergency ballast blow. High-pressure air forced water out of the ballast tanks, and the 6,500-ton Leviathan shot toward the surface. It took only 11 minutes for the submarine to rocket from depth to the surface, breaking the waves in a cloud of foam and steam. For the next 6 hours, the titanium beast fought to stay afloat. The fire burned so hot that the rubber anechoic coating on the outer hull began to peel and smoke. But the heat had destroyed the integrity of the aft seals. Compressed air systems failed. Water began to force its way back into the stern compartments. The center of gravity shifted relentlessly aft. The buoyancy that had saved them 11 minutes earlier was now being erased by the weight of the flooding. Survivors in the water witnessed a sight that defied the logic of naval architecture. As the stern lost its fight with Archimedes, the bow rose higher and higher. One survivor later described the 8,500-ton vessel standing vertically in the water like a giant cigarette. For a few seconds, the submarine hung there suspended between the atmosphere and the abyss. Then gravity won. The boat slipped backward beneath the waves, beginning a long, silent fall to the bottom. She did not stop falling until she hit the seabed at a depth of 5,510 feet. The impact was massive, but the titanium hull held its shape. The Komsomolets was gone, but she was not finished with the world. She carried a payload that transformed her from a shipwreck into a ticking environmental time bomb. In her forward torpedo room, she carried 2 nuclear-tipped torpedoes. In her stern, she carried a nuclear reactor core loaded with uranium. For the last 3 decades, that payload has been sitting in the dark, subjected to pressures of over 2,400 pounds per square inch. The salt water is eating at the containment. The titanium is resisting, but the seals are not. The Cold War is over, but the battle to contain the radiation inside the Komsomolets has just begun. The question is not if she will leak, but when and how much. To understand the scale of the threat, we must first understand the impossible environment where she rests. 5,510 feet. That is the number that defines the physical reality of the Komsomolets. To understand why this wreck is such a mechanical anomaly, you have to look at the engineering limits of the Cold War. In 1984, this submarine set a world record for combat vessels by diving to a depth of 3,350 feet. That was considered the bleeding edge of naval architecture. It was a depth where the ocean exerts over 1,500 pounds of pressure on every square inch of the metal. But the wreck sits far deeper than that. When she sank, she plummeted past her calculated crush depth. By all conventional logic, the pressure hull should have buckled and imploded like a crushed soda can long before she hit the bottom. The math dictates that a pressure hull typically fails catastrophically once it exceeds its design limit by 50%. Yet the sonar images and the camera feeds tell a different story. The main pressure hull of the Komsomolets is almost perfectly intact. The secret lies in the metallurgy. The Soviet Union invested massive resources into Project 685 to create a hull made entirely of titanium alloy, specifically a mixture known as 48T. Titanium is roughly 40% lighter than steel, but significantly stronger. It is also non-magnetic, making the boat invisible to magnetic anomaly detectors. But its most ghostly property is visible right now on the ocean floor in the harsh lights of the remote-operated vehicles. Deep sea salvage experts call it the titanium paradox. Down in the darkness of the Norwegian Sea, the salt water and the pressure are aggressive enemies. If this were a steel hull like the Titanic or the Bismarck, the metal would be covered in rusticles and bacteria eating away the iron. But the Komsomolets glows in the darkness. The titanium panels look as bright and clean as the day they left the shipyard in 1983. The steel components around them, such as the outer railings and the hydroplane mechanisms, are rotting away, turning into orange dust. But the central cylinder, the shield guarding the reactor and the torpedoes, remains pristine. The water pressure at this depth is roughly 2,450 pounds per square inch. Imagine a heavy-duty pickup truck balanced on every single square inch of the hull surface. That is the force keeping the Komsomolets pinned to the silt. This structural resilience creates a unique problem for any potential recovery. The hull is too strong to be crushed, but it is also too heavy to be lifted. The sheer mass of the titanium combined with the extreme depth makes a physical recovery operation functionally impossible. We do not have the crane capacity to lift a 6,000-ton dead weight from over a mile down without risking a catastrophic cable snap. The Komsomolets is not just a wreck, she is a permanent resident of the abyss. However, while the titanium shell is holding the line, the soft parts of the submarine are not. A pressure hull is only as strong as its penetrations. There are cooling pipes, wire pass-throughs, and torpedo tube hatches that rely on rubber gaskets and hydraulic seals. These materials were never designed to last decades under such crushing weight. The hull is a fortress, but the gates are beginning to fail. And inside that fortress, the seawater is finding things that should never be wet. This brings us to the true danger. The titanium can last forever. The nuclear warheads inside cannot. The physical impossibility of the hull survival has created a containment vessel that is slowly filling with water. And as the surveys would discover, that water is beginning to carry a toxic signature out of the boat. The clock is no longer ticking on the structure, it is ticking on the chemistry inside. 2025. That is the number that has haunted the salvage engineers for decades. It is not a depth and it is not a coordinate. It is an expiration date. When the Soviet Union collapsed and the Russian Federation took over the custody of the Komsomolets, they faced a terrifying reality. In 1994, a survey team discovered that the seawater was already breaching the titanium containment. The two nuclear-tipped torpedoes in the bow were corroding. The plutonium inside was beginning to leach into the ocean environment. The engineers at the time lacked the budget or the technology to raise the boat. Instead, they chose a strategy of containment. In a series of high-risk expeditions between 1994 and 1996, they descended to the wreck with a specialized chemical payload. They could not weld patches over the torpedo tubes at that depth. The pressure was too great and the environment was too hostile. So they improvised. They covered the breaches in the bow with a specialized rubberized blanket, and they injected a jelly-like sealant into the torpedo tubes. This chemical barrier was designed to harden and isolate the warheads from the flowing current. But the engineers knew it was not a permanent solution. The technical documentation for the sealant gave it a functional lifespan of 20 to 30 years. That clock started ticking in the mid-90s. By simple arithmetic, the guarantee on that chemical patch runs out roughly around the year 2025. The containment system is currently living on borrowed time. In 2019, a joint Norwegian and Russian expedition returned to the site to audit the status of these patches. They deployed a remotely operated vehicle known as the Aegir 6000, a machine capable of precise maneuvering at extreme depths. The mission was to take water samples directly from the ventilation pipes and the torpedo tube apertures. They needed to know if the jelly was still holding back the plutonium. The results were sobering. When the researchers analyzed the water samples taken from a ventilation pipe near the reactor compartment, they found cesium-137. The levels were not just elevated, they were astronomical. The sample showed radiation levels 800,000 times higher than normal seawater. The number is staggering. It confirmed that the reactor compartment is no longer a sealed system. The seawater is circulating inside the core, washing over the nuclear fuel and carrying radioactive isotopes out into the open ocean. However, the ocean is vast. The physics of dilution are working in our favor for now. The expedition team noted that while the concentration at the pipe exit was lethal, the levels dropped to near normal only a few feet away. The massive volume of the Norwegian Sea is acting as a heat sink, absorbing and dispersing the poison. But the presence of such a concentrated stream proves that the 1990s era fix has failed. The interior of the Komsomolets is now open to the sea. This creates a new and volatile dynamic. The chemical sealant is failing just as the titanium hull continues to resist corrosion. This means the boat is becoming a pressurized bottle of radioactive water. The structure remains intact, but the contents are leaking out through the vents. And as the camera drone moved along the hull, it captured something else. It was not just an invisible reading on a Geiger counter, it was a visual confirmation of a failure that the engineers had feared for 30 years. The most haunting feature of the Komsomolets wreck is not what is there, but what is missing. When you look at the sonar scans of the sail, there is a massive rectangular void in the center of the structure. It looks like a bomb blast or a catastrophic structural failure. In reality, it is a perfectly functioning architectural feature that represents one of the cruelest logical paradoxes in naval history. This void is the housing for the VSK emergency escape capsule. It was a detachable lifeboat built directly into the sail designed to save the command crew in the event of a total loss. On the day of the sinking, Captain Evgeny Vanin stayed aboard the submarine until the very end. He remained in the control room coordinating the damage control efforts while the rest of the crew abandoned ship into the freezing water. When the stern finally dipped below the surface and the boat began its terminal plunge, Vanin and 4 other crew members were trapped inside. Their only option was the capsule. They climbed into the small titanium pod, sealed the hatch, and triggered the explosive bolts to separate the capsule from the sinking submarine. Mechanically, the system worked. The capsule detached from the hull, which was already sinking deep into the abyss. The buoyancy of the pod took over and it rocketed toward the surface. But the physics of a rapid ascent from deep water are violent. As the capsule breached the surface, the internal pressure difference caused a catastrophic failure. Reports describe an event similar to explosive decompression. The hatch assembly failed violently. Of the 5 men inside, only one warrant officer, Slyusarenko, was ejected alive into the sea. Captain Vanin and the other 3 men died in the capsule, either from the pressure trauma or from drowning as the pod flooded and sank back down in the rough seas. This creates a grim statistical reality. The escape capsule was the most advanced safety system on the boat, yet it had a survival rate of only 20%. Meanwhile, the crew members who had abandoned ship earlier were fighting a different enemy. The water temperature in the Norwegian Sea was freezing. They had to wait 81 minutes for the factory ship Alexei Klobostov to arrive on the scene. In that hour and a half, the cold claimed dozens of lives. By the time the rescue operation was complete, 42 men were dead. The capsule, which was designed to be the ultimate guarantee of survival, became a tomb. Today, that empty space in the sail serves as a permanent scar. It allows the current to flow through the center of the fin, whistling through the titanium framework. It is the most obvious damage on the upper profile of the wreck. But if you move the camera forward along the deck, you encounter a different kind of damage. The sail is intact save for the missing capsule. The hull plating amidships is smooth and unbroken, but the bow is a disaster scene. The forward section of the outer hull is crushed and torn. The deck plates are buckled upward and the nose of the submarine looks like it was smashed by a giant hammer. This damage profile contradicts the narrative of the sinking. We know the fire was in the stern. We know the boat sank tail first. Logic dictates that the stern should be the most damaged section and the bow should be relatively pristine. The fact that the bow is crushed implies that something violent happened during the descent, something that the fire alone cannot explain. To understand this wreckage, we have to look at the hydrodynamics of a sinking ship falling through a mile of water. The damage to the bow presents a contradiction that has puzzled naval architects for years. When the Komsomolets died, she sank stern first. We know this from the testimony of the survivors floating in the freezing water. They watched the bow rise vertically into the air, standing like a monolith against the gray sky before slipping beneath the waves. In a standard shipwreck scenario, the part of the ship that hits the bottom first absorbs the impact energy. By that logic, the stern should be a crumpled accordion mess, while the bow should be relatively intact. But the forensic video reveals the exact opposite. The stern is buried in the mud but appears structurally sound. The bow, however, is shattered. The outer hull plating is ripped open, and the deck plates are buckled upward as if an explosion occurred inside. The explanation for this reversal lies in the brutal physics of hydrostatics. It comes down to the difference between a flooded compartment and a dry one. When the submarine sank, the stern compartments were already fully flooded. The water inside the engineering spaces was at the same pressure as the water outside. There was no pressure differential, so the hull had no reason to crush. The steel and titanium simply existed in equilibrium with the sea. But the forward compartments were different. As the boat began its long fall to the bottom, the bow was still full of atmospheric air. The crew had sealed the watertight bulkheads to keep the boat afloat. Ironically, that act of damage control doomed the structure of the nose. As the boat passed the depth of 1,000 feet, the ocean was pushing against the hull with 440 pounds of force per square inch. The air inside was pushing back with only 14 pounds per square inch. The titanium pressure hull was strong enough to win this contest, but the lighter outer hull and the sonar dome were not. At some point during the descent, the pressure difference became mathematically unsustainable. The air pockets in the bow imploded. The sea hammered the plating inward with the force of a hydraulic press, smashing the outer casing and tearing the deck structures apart. This is not just a cosmetic injury. This crushed section houses the torpedo room. Inside that twisted metal are the two nuclear-tipped torpedoes that serve as the primary concern for the environmental monitors. The collapse of the outer hull has removed the physical barriers that shielded these weapons from the open ocean. The warheads are now effectively exposed to the circulating current, and we know that the current is flowing through the wreck because the remote-operated vehicles have seen it happening. During the 2019 expedition, the cameras captured one of the most unsettling sights in modern shipwreck exploration. As the lights swept over a ventilation pipe connected to the reactor compartment, they illuminated a strange phenomenon. It appeared to be a cloud of gray smoke puffing rhythmically out of the pipe. At first glance, it looked like the submarine was still running venting exhaust into the water. In reality, this was the cloud. It is a plume of silt and radioactive water being pumped out of the hull by the ocean currents. The wreck is breathing. The tide pushes water into the crushed bow and the open hatches, and it forces that water out through the vents, carrying particles of the interior with it. This pulsing stream is the visual proof that the Komsomolets is not a sealed tomb. It is an active part of the ecosystem exchanging fluids with the sea. The bow is crushed, the reactor is venting, but there is one part of the ship that remains seemingly untouched by the violence of the sinking or the corruption of the radiation. At the very end of the ship, buried in the silt, lies a piece of engineering that looks like it was installed yesterday. The propeller of the Komsomolets is a piece of sculpture in the deep. If you look at the footage from the stern, you can see the massive bronze blades rising out of the sediment. The metal is uncorroded. Bronze is an alloy that naturally resists the chemistry of salt water, and here in the oxygen, poor environment of the deep seabed, it looks almost new. It is a stark contrast to the violence of the crushed bow. The stern is peaceful. It rests in the mud as if the submarine is simply parked waiting for the order to start the turbine. But if you look closely at the horizontal stabilizers near the tail, you will see a detail that confuses many observers. Mounted directly onto the flat control surfaces are two shapes that look like short, fat torpedoes. They are cylindrical with rounded noses, and they seem to be attached to the hull like parasites. In the comment sections of shipwreck videos, these are often mistaken for external weapon pods or sensor arrays. They are neither. These are the auxiliary propulsion gondolas often referred to by naval engineers as creepers. They represent a specific tactical philosophy of the late Cold War Soviet Navy. The Komsomolets was a nuclear boat designed for high speed and deep diving, but a nuclear reactor requires coolant pumps and turbines machinery that makes noise. In the deadly game of anti-submarine warfare, noise is death. These small electrical thrusters allowed the giant submarine to shut down her main noisy propulsion train and creep through the water using battery power. It was a mode of travel designed for total stealth, allowing the boat to hover or move at very low speeds without turning the massive main screw. It is a bitter irony that a machine built for absolute silence is now achieving that goal permanently. The creepers are motionless. The main screw is buried in the silt. The only sound at the wreck site is the whirring of the robot thrusters sent down to watch it die. The decision to leave the Komsomolets on the bottom was not made lightly. For years, the Russian Federation debated the possibility of a lift operation. There were plans drawn up to cradle the hull in a massive lifting claw or to fill it with buoyant foam to float it to the surface. But every engineering simulation ended with the same conclusion. The risk was too high. The hull is strong, but it is also heavy. The structural integrity of the internal frames is unknown. If the hull were to snap during the ascent, it would release the nuclear inventory, instantly turning a slow leak into a catastrophic plume. Furthermore, the wreck is a designated war grave. Of the 69 men who sailed on her final voyage, 42 remain on eternal patrol. Most of them died in the freezing water waiting for rescue, but their ship remains their headstone. So the strategy has shifted from recovery to surveillance. The Komsomolets has become the most closely monitored shipwreck in the world. She is visited regularly, not by salvors looking for treasure, but by scientists looking for cesium. The sensors are placed, the samples are taken, and the robots leave. The lights fade, and the titanium boat returns to the darkness. She remains a paradox of the Cold War. She was the deepest diving combat submarine ever built, a pinnacle of titanium engineering that cost a fortune to construct. Yet she was brought down by a 50-cent electrical fault and a fire that could not be contained. She is a nuclear fortress that is slowly leaking poison. She is a tomb that is still breathing. For now, the ocean is diluting the threat, but the engineers are watching the clock. The Komsomolets is sleeping, but she is not dead.